nice introduction. I'm actually 38. That was the only thing I wanted to correct. The rest was, exaggerated, but it's always nice. By the way, before I start, indeed, this is the only slide where I have the network center.nl. Perhaps after the talk, if you have time, just look there. This is a big initiative, this place here. And we're trying to do something in the Netherlands as well, to create more energy, more funding for network theory. I'll talk about joint work, indeed, with Remco, you already mentioned. Clara, she's in the lead of this topic. Guido Jansen, also from the same university, and I'll present in particular this recent archive paper. It's a couple of weeks old. First presentation I give about the work, and in the second part of the presentation I'll talk about two more subjects that are related to this and that will be out at the end of the summer. So the topic will be clustering in the most basic form. What is the probability that two friends of yours connect with each other? So that's what we mean by it. I'll look at scale-free graphs, so you all know what I mean by that. And somehow I want to make a vague, but at least mathematically concrete connection with hierarchy. So that's the goal of the talk. But let's just start. Is the talk like 1 hour? I mean, check.
1 hour, yeah.
Okay, perhaps it's a bit shorter, but we have enough time. So local clustering, that's the notion I'll be using. And this is quite essential for the talk because there are quite a few definitions of clustering around, global clustering for instance. But what I mean is really local clustering. Take any degree, any node in the network of degree k, look at two of its neighbors, and then ask the question, are these neighbors connected? So that's what I mean by local clustering, and it's a function of the degree of the node. Yeah. So we've called it clustering spectrum if you plot this function from k to ck. So here you see an example. I think this is I'll show you a few more examples, but this is the YouTube network, so friendship relations is there. Quite a big network. Here you see on a log scale the degree of the nodes, and here you see there's some bins here, but we plot the probability of nodes having degree, let's say 10, of forming this triangle with friends. Yeah? So this definition applied to nodes, and then you get a curve like this. And we've plotted many of these curves, and in fact, in many network papers you see these curves being plotted. I'll show you quite a few of them later on for the largest data sets we currently have. And the larger the data sets, the more pronounced certain effects seem to be. So, but perhaps I should ask you that question. So, what would you observe if you see this YouTube data? Can you throw a couple of observations at me? Yeah, I think that's the main observation. So you see like a decay. You see more than that? You recognize two regions. You mean here and there? Yeah. So definitely there seems to be a threshold. This is just one data set, so you can't really draw firm conclusions about that. There seems to be a power law there. That's the red line. It's just basic stats and didn't do a good attempt to make it fit, but you could believe that there's a red line. And definitely this part is a bit flatter than that part. Okay, so I guess now here you see some all the references already now that looked at this local clustering and also made a connection with hierarchy. Perhaps before I go into our analysis, I'll try to explain that point. But everybody's with me now that we're talking about this object. That's the sole object I'll be talking about in the first half of the talk. Good. So hierarchy, I'll try to explain. So we have this spectrum which seems to be flat and then falls off, and you see that in many data sets. And this is some sort of a hierarchy. So this is not a really complex network. This is the LinkedIn network of one of the authors. But after searching for communities or groups, and making a nice visualization, you see some kind of a jellyfish octopus type image. So it's just to demonstrate the idea behind the hierarchy. So what could this dropping spectrum mean? Well, for instance, it could mean that the high degree nodes, the hubs, have a hard time forming triangles. And one way to envision how this could arise is that these hubs, like the legs of a jellyfish, interconnect groups or communities. And within these groups, there's an abundance of triangles. These are people that know each other. So somehow, the people that are typically extremely dominant in skill-free networks now seem to be prevented from making triangle connections. That's what the dropping spectrum says. And we have no results on this, but this is a mental picture that we have and quite a few others have. And this is something you could call hierarchy, although you could also define it in different ways. And so this is just to give you a flavor of the picture I have, at least, when I talk about that spectrum. Okay, then the model. So I hope quite a few of you are familiar with this model. It's the hidden variable model. It goes by many names, actually, in the literature. And I would say it's mathematically the most tractable model when you deal with skill-free networks. So how does it work? We build a random network out of n vertices. Each of these vertices gets an IID weight drawn from some distribution. And then you start connecting these vertices according to a function of these two weights. So you have a vertex with weight h prime, and then there's a connection probability p h prime that tells you whether there will be an edge or not. I'm going to work with this function, but that function is an instance of in fact, a much wider universality class of functions you can choose. So the results I'll present will also hold for different functions that are asymptotically, when n gets large, behave similarly. And do notice that this is a probability, so I won't go further than 1. That's when then there's a full stop and then the edge is there. So here you see an example, 7 nodes. They each got their own weight, hi. So you see the weights here. And then the algorithm to construct the network is just pairwise, draw the edge or not. And you also see that, for instance, this node had a high degree. It ends up being connected to 2 other vertices. It had a weight of 3, and we choose the weights such that they are at least an expectation matching the degree. So whenever you see weight h, think of degree k, but of course it doesn't need to be one-on-one. Okay, now scale free. So we will choose the weight or degree distribution according to power law, and Dima just told me before the talk that it's better to use a gamma here. So I hope you can digest that. So I'm going to use a tau. And the tau is strictly in between 2 and 3 because the results I'll present will be quite meaningless for tau bigger than 3. So it's really skill-free setting. And that's how we're going to work. So Bayan Baguna and Pastor Satoros, they've coined this model hidden variable. In the more combinatorics community, people call it the inhomogeneous random graph. And then there are lots of generalizations, and some of you might also know this model going by the name of the Chang-Lu model, who had done some of the earliest work on it. Yeah, so that's the setting. Are there any questions about the model? No? Okay, let's continue then.
One comment that in Chang-Lu, she was not drawing that from the distribution.
No. Yeah, that's true. But I think this is nowadays also called Chang-Lu model. Yeah. Okay. Good. Okay. So this is the final time I'll make this point. But in the paper we make the connection between H and K rigorous. You'll see in the formulas that it's much nicer to work with H, so the weight, instead of the degree K. But for now you should believe me that we can replace, whenever we look at the CK, we can replace it by CH, which means that two neighbors of an H vertex with weight H, are connected. So it's the exact same definition, but I'm going from degrees to weights. And in fact, that's the main step that makes the hidden variable model nice to work. And how good the approximation is, and in fact, if there's a asymptotic agreement, that requires work typically, but okay. Now, you see the triangle. This is our main object. We start from one vertex that has a given degree h, so then we're on the horizontal axis of our spectrum. We go to two other vertices that have degrees h prime and h double prime, and then the local clustering, that probability that these two other vertices are connected, is given by this simple integral. So integrate over all possible values that these neighbors can have. So you see here and then conditional on being connected to H, you want being connected to this vertex, you want to establish that connection. Same here, so those are these two lines, and of course these two neighbors then also need to be connected. And so that's what you want to calculate. And if I remove that condition, then you get this integral. Yeah, so draw from the weight distribution twice to generate these weights. Connect all three of them, and that's a normalizing constant. So the main object now will be to analyze this integral. You see where the integral comes from? Yeah? It's very intuitive. Eh? And this is just the exact formula. There's no asymptotics here. If you're willing to accept that degrees are weights, this is the local clustering function. And now it boils down to understanding what happens in the large limit. Okay, so this is the main result of the talk, visually. So we've recognized some of these elements already in that YouTube data set. What I'll show you, and I'll try to argue it in a bit of a physical way so that we explain why this is the case. There are three ranges, 1, 2, and 3. In the first range, the local clustering remains flat, which means that whether you build a triangle is quite independent from who you are, as long as you are not too well connected. Okay? Then we identify the first threshold, which is n to the tau minus 2 over tau minus 1, which is always smaller than square root of n for the scale-free range we're interested in. From that point onwards, you'll start dropping. So somehow you start feeling restrictions of making these triangles. So you as a degree h node, you start feeling some kind of structural correlation that makes you less well equipped to establish that type of connection. Then you go all the way up to square root of n, quite a meaningful threshold in network theory in general. Some people call it the structural cutoff. And from that point onwards, you settle on the power law that we'll make explicit in a minute. And this goes all the way up to the natural cutoff and to the 1 over tau minus 1, which is the extreme value you would get if you sample from a power law distribution with exponent tau. You could continue, but there will be nothing much meaningful afterwards. So if you set up the random graph like the way we do, then this is almost the final end of the relevant range of weights. So perhaps before I give the formulas, so we're going to settle on a certain power law there. Is there somebody who knows what this number should be? So what should be the exponent of this part? Or could you guess what it is? Or have you seen it? Any guesses about that? It's actually reported quite often in the literature, not necessarily for this model, but for various models, people have investigated this. Nobody's daring to guess? Dino, did you guess? Oh, we talked too much about this stuff. You're part of the play. You're part of the play. Yeah.
Like, is the considering normalized one, or is it the raw number of trying?
It's the raw number. Yeah. It's no normalization. But in fact, there's quite a strong consensus, and not necessarily consensus, but a first guess of what people believe, that this falls off as 1 over h. Yeah, so that's roughly true, but for this simple model, it's definitely a bit more richer. But I'll show you, I think, on the next slide. Yeah, so this is the picture of the main result.
When you do a random graph, I know you also have, well, no, actually, sorry, I was trying to remember, if you do just an average value, and then you calculate the clustering, you don't get any power on that.
No. So the problem with that is that this loses its meaning because the scale-free notion is very important for this spectrum to arise. Yeah.
With the preferential attention plane, then you get a power number.
Yeah, I think if you fit PA to gamma is 3, you get a precise 1 over k follow-up. So that definitely stimulates the consensus or conjecture. Yeah, that's a good point. Okay, so let me translate this picture into formulas. So it looks like this. So this means proportionals. I'm dropping the constants or something which is not dominant. If you're below that threshold, you don't see any dependence on h. So that's the first flat part. Of course, you do see non-trivial dependence on n. And in fact, quite a few people are also interested in this type of behavior, especially when tau gets close to 2. A lot of relevant networks are close to 2, then this becomes slow. So for very, very large networks, although clustering is diminishing, it's likely to be present. But it has, for this talk, I'm not too much interested in that. I'm only looking at the h. Where is the h? So this I call flat, although still it's dropping away. Here you see a very mild dependence on h, so that's where the flat part starts curving. And there you see the final power law. And the exponent effect is -2 times 3 minus tau, which means for tau is 2.5, you have the -1. But for tau is 2.2, it would be 1.6. So it will fall off quicker than you might expect from other models. Okay. I'm not saying in real data sets it falls off quicker, right? Just to make that point clear. But definitely with this simple model, you would think that the fall-off increases when tau approaches 2. Yeah, so I'm now trying to work my way to explain to you how you get these formulas. And it has a lot to do with structural correlation. So remember, this is the connection probability I'm using. Mu, by the way, is just the mean degree. And what you immediately notice is that if you start building edges with these probabilities, that if you are a node that is smaller than this threshold, that was the first threshold we saw, then you can connect with all the other nodes, all the way up to the maximal value that you most likely will encounter, without putting a 1 there. So without any interference of the network, you would say. Yeah? That's actually a very important step to understand the ranges. So that's why this is quite intuitive, this threshold. If you go beyond that, you see that if you multiply an h prime value and this h value, that at n over h, when h prime takes that value, then you hit the 1. And you can't go beyond that. So that means that from this point onwards, you just have that edge, and that's it. There's nothing added to it. And that's a big difference with several other random graph models, like the configuration model. So for those of you who don't know that model, you can also build a scale-free network with that model, but it will build a lot of connections between high-degree nodes. And here, there's only one edge max. There's either an edge or not between any pair of nodes. So I think the spectrum that I'm showing you today has a lot to do with single edge constrained networks. The moment you allow for an abundance of connectivity, reasonings could be different. But because we can only build one edge, this is of course a very important point and likely to be a transition point. So we call this in our paper structural correlations, because somehow you started locally, you attach to other people, and now you start feeling, restrictions, correlations, right? So because you want to go there, but you can't really. Okay, I hope that's clear. So, some observations about an important trade-off that's related to this. So, if you look at scale-free networks, you're dealing with power law degrees, and high-degree nodes are extremely important. I mean, they dominate almost all aspects of these networks, but they're also rare. I mean, that's why they're so important. They every now and then occur. Especially the nodes with degree n to the 1 over tau minus 1, they're very rare. If you run a simulation, it takes a while before you'll come across them. On the other hand, this connection probability doesn't really care that much about it, because it decreases only until it hits a certain maximum value, so that the product of H and H prime is the number of nodes in the network N. So that's this observation, and therefore, and I'll make this point a couple of times more, is that in the analysis that we're after, so calculating things about the local clustering, we can really stop at that point. So it means that we kind of rule out connections with high-degree nodes that are likely to be out there, and that's structural correlation. That creates a trade-off. I mean, on the one hand, these high-degree nodes are very important. On the other hand, the connections that we're going to make, you're only going to make one connection if you get a chance, and that's it. So you can't go. It has a limited impact. Yeah. So also in formulas, this will come back. The sketch of the proof. So remember, perhaps I should have repeated it, but we are about to analyze the double integral. Double integral of H prime, H double prime, and then these three connection probabilities. That's what we want. So when I'm below that first threshold, then there are no structural correlations. So if I'm asking about whether this edge is present or not, I can just do that. When I'm in between, so this is range 1, and there's nothing special about that range. That's why it's going to be flat. If I'm in range 2, so that's the logarithmic type decay, then the structural correlations start to enter, because whenever I am in between these two values, then I will be meeting correlations with other degrees that are bigger than square root of n. Yeah, because of that min function. So even these other two might be above that threshold and experience structural correlations themselves. So in all three edges, I'm getting structural correlations that I could be restricted. And that's actually the most nasty calculation. So that's this part until we hit the power law. The final part, if I'm below square root of n, then I will have structural correlations with these other two that need to be smaller than. So that means that these two, they will be restricted. And now this is like what I said, a bit more of a physics intuition behind this triangle. It also just drops out of the calculations that you do on the integral. So naturally you'll come across these three ranges, but they'll have a meaning. Yeah? So they have these meanings that small nodes, you only matter about possible correlations among the others. Here, they could all be, let's say, at risk or under pressure. And here, because you yourself are big, there's a possibly negative correlation with the two neighbors. Okay. Now, another way to understand our result is to think in terms of most likely triangles. And And that will also be a natural bridge to the second part of the talk. So if you are small, so if you're smaller than square root of n, then what comes out of our analysis is that the two neighbors that you have together multiplied will be of the order n. Yeah, so that's again has to do with the fact that they're completely free to do whatever they like. And in fact, when you look at what the most likely triangle will be, so in terms of the probability that a certain triangle with certain weights will be created, then these are conditions that arise. If you yourself are bigger than the structural cutoff, then these two nodes need to be smaller, they're restricted. And in fact, the most likely triangle, and I'll also go to brackets and motifs at the final part of the talk, will be square root n, square root n, square root n. That's the triangle that has the biggest chance of being seen in the random network. Okay, let's, before going to other formulas, let's look at some data. And by the way, this is an open invitation just for my own sake, but I know that a lot of you guys are working on complex network theory. And if you have a different data set and you want to test, for instance, how the local spectrum, clustering spectrum will look like, I'm very much interested in this. So we decided to go by these data sets. These are some of the biggest out there currently. Perhaps you recognize them. I don't even know all the details myself, but these are publicly available. And there are some technological networks, some social networks. But look at the nodes. They're all of a considerable size. 100,000, a million order. A good number of edges. And they're all scale-free with a ranging exponent. And here you see the estimates, I'll show you the pictures in a minute, of the alpha, which is the exponent of our spectrum. Yeah, so there's definitely not I'm definitely not going to say anything very convincing about that. That if you would take a data set of 1 million nodes, and you would statistically estimate, well, first the tau, then the alpha, this is going to be notoriously difficult to do this in a decent way, that then this alpha would correspond to the thing that I just showed you. That's not what I'm claiming. But I'll get back to that. This is just what we did with plain statistics. Just to show you a few pictures. And the question, of course, is, and we didn't really manipulate this, we just took all the data sets we came across that are reasonably sized. And they all look quite similar. They are put in this order. So, except for the YouTube thing, you saw that in the first slide. So there are 9 data sets. And you see a couple of interesting things. Obviously, they won't display this perfect spectrum I just showed you. So flat, logarithmic, power law follow. But they have some similar features. I'm not so much interested in these values, by the way. I'm only interested in the function of h, so the spectrum. And many of them have a relatively flat range. The threshold is quite clearly visible, and for most of them, you could go by guessing that there will be a power law, but this is of course not completely clear. And if you look at our analysis, one thing we also showed, which is a bit of not necessarily negative result, but definitely if you want to get the power law right, the exponent, you need very, very big networks. So 1 million nodes for the asymptotic theory that we're employing is by far not enough. What we can argue is that if you look at bigger and bigger networks, then the fall-off will be more and more steep. So, for instance, if you believe that your network would have a fall-off of 1.3, then it's expected that if the network grows, then it's slowly moving from 1.1 up to 1.3. But our calculation seems to indicate that even these networks are not big enough to really see the real asymptotes behind it. Also, the model could be off, of course. I mean, this is just a simple model for a complex network. On the other hand, so that's the downside. I think I should start with it. On the other hand, we were quite excited when we saw this, when we had the formal picture of that spectrum clear. Because and it depends a bit on how opportunistic you are. But if you're willing to believe in something like this, and you see these pictures for this data set, and you see more and more data sets, there is something in it. It's not that we're explaining everything, but Dima, you have a question.
Those straight lines, are they just fits or are they given by your alpha based on the time?
No, that's a good point. So, and actually that's also a disclaimer. These are just statistical estimates, so just fits. And if I would make the mapping, so just estimating tau and then come up with alpha bar, this is not a good match. So there's definitely nothing spectacular there. Yeah. It's just that perhaps at this point then it's more about structural properties. It seems to be flat. You could pinpoint one or two thresholds there, and there's definitely reason to speculate that there's a problem. Yeah. More questions about it? That's a good point. Okay, now I'm gonna. I think this was kind of half of the presentation, and the second half I'll jump quicker through several topics. So you can also skip one of these topics if you feel like it. For instance, the first one, configuration model. For those of you who've not seen how it works, the configuration model just also takes n nodes, but samples degrees. The degrees start out as being half edges or stubs, and then uniformly at random you start selecting pairs of stubs and connect them until you get a random network, and you keep doing this over and over again. Erase means that in this way, of course, you can build double edges, but these double edges, multiple edges, can become extremely dominant in scale-free regimes. So a good candidate model for a complex scale-free network is the erase configuration model, where you only hold on to one of these edges. And for instance, if there were 7 more between these two nodes, you kill them. Yeah, that's the erase configuration model. If you want to know things about that, Pim is one of the experts working on it. So here we go, that's the algorithm. So those two stubs were selected. Those two, so this is a 5-node network. I'm not happy with that one, so I killed that one, and the cell group was also erased. Yeah? So this is an outcome, and then we want to study the statistical property of this. Okay, now in the erase configuration model, so ECM, erase configuration model, the probability that there's no half edge of I connecting to a half edge of J, you could write like this. There's a degree I for node I, so you need to be unlucky di times. And if you want to look closely, you recognize that. And then you're very much entering the framework of the hidden variable model again, because this is a connection probability that takes a di and a dj and builds a connection. So there's a very natural connection here, except the mathematics you'll need is very different. I like, just to be fast, I like the integral better, which immediately can let you do calculations. Here you need to be much more careful, because there will be indicators in the expression, because it should be actually there, right, the connections. But at a higher level, you could also argue that these should be the same model. So we set out to study this model as well, and hope to find the same clustering spectrum. And if that's the case, that's the first sign of universality, which is good. The two standard models have the same spectrum. I gave away already the punchline, of course, there will be the same spectrum. This is one of the papers which is almost done. The mathematics is a bit more nasty, but I'll say a few more words about it. So this is what I've just explained. And if you now see degrees here, you should think about these weights. So you just put them in that function. That also means that you could have comparable spectra, and it's a slightly more difficult one. So this is a repetition of what I just said. And yeah, I didn't want to spend too much more time on it. It's a really nice paper, we feel, but let's say the main insights have been observed already in our first paper. So we'll show that in the ECM, we get the same 3 ranges and the same type of behavior. Okay, now I'm going to take one step back and look at the average nearest neighbor degree. And then if I'm good with time, I'll also go one step up and look at graphlets at the final part. But first, average nearest neighbor degree. So we started this talk with the triangle. Now no longer it's in the triangle, but just in one edge. I have a certain degree or weight. I connect to one of my neighbors, and what is the degree of that neighbor, on average. Okay, so there's also very recent work of Pim, who's sitting here in the front. Very nice paper. There's a connection with what I'll show you, except in this line of reasoning, we'll scale k as a function of n, and Pim proves several limit theorems for fixed k. Is that put correctly?
Yeah.
But I've put it up here because it's recent and interesting to look at. So hk, average nearest neighbor degree. Note that there's now a k again, so this is a real degree, but I'll replace it by an h in a minute. So I have k of these neighbors, so 1 over k. For each of these neighbors, I ask, am I connected to them? And if I'm connected to them, I count their degree. That's it. Yeah? So I start from here, I branch out to all of my neighbors, I ask, what is your degree? And I take the average. Okay, this is the spectrum that we found. It's not published yet, and it's not necessarily easier or difficult than the CA spectrum, but it's just different. Obviously, it shares some features. That's why I'm putting it up here. So now there are two ranges. We again see that threshold n to the tau minus 1 over tau minus 2, the other way around, square root of n and the extreme value. And then there is a major difference, which might start playing a bigger role in future work. So we again prove flat range. This is flat range, and decaying range. And here you see the exact decay and what it is. But the way we prove it is now different. So for the triangle, we everywhere have the same type of convergence. For the AND function, this AK function, we also have the expectations. You see them here and there. But in the lower region, we go to a stable distribution. So not only a constant, but multiplied by a stable distribution. This typically means trouble. And for the higher region, the structural correlations kick in, and they let us converge nicely to a constant. So it's not, I mean, the terminology is a bit strange, but some people, I would say, would call this non-self-averaging. And it means that these nodes, these neighbors, get so much freedom, they'll draw from power laws, and power laws means that you can't control the natural fluctuations of the object you look at. So if you would sample this over and over again, you would get a lot of noise, not self-averaging. Here, because you enter the zone where you're gonna get stuck, it will be a more stricter result. Yeah? So you could find this more interesting or that. I'm not gonna put a qualitative stamp on it, but at least it's something we've detected. And perhaps it's also known, I don't know yet, but it's something that comes out of our analysis. Okay, this doesn't matter. I think you're willing to believe me. So I just replaced the wall of k by h, but by now we've also done this for the ECM model. So you can also do it with the k, but then for ECM. Yeah, I'm going to skip this in the interest of time. I just explained that with hand waving and give you the trade-off. So look at this formula. Perhaps I should explain it once more. So 1 over h, this is kind of the number of neighbors you have. This is the weight of your neighbor, and of course you need to connect to that particular neighbor. Now here's the trade-off. If the hj's, so that if your neighbors are quite big, then of course you'll connect easily to them. Yeah, so that's the connection probability. This I've explained earlier. It only increases until that threshold n over h. So at some point it won't matter that this is a powerful neighbor. You've connected to it. That's it. There's no added value. Do note again that power law degrees are dominant, but rare. And you could ask, what is the maximal contribution that I'll get? So on the one hand, you want to connect to big vertices, nodes, because they easily make connection. And if you statistically sample them, think about running a simulation here, and you don't have enough of them. And the product, of course, matters. How likely do they occur, and how easy can I make connections? And there's a trade-off. And the natural point, again, is n over h. Let's look a bit more closely at this, if time permits. I don't know how I'm doing in time. There's no clock here.
We have like 10 minutes.
10 minutes, that's good. But I need to speed up a bit. How many vertices are actually of that order? N over h. So if h is square root of n, I'm asking how many vertices are of order square root of n, multiplied by a constant. So I integrate over the distribution, and you can see that it's this order. So I add a 1 there, so it's in fact order 2 minus tau h tau minus 1. That's just given from the model. Now if I'm bigger than that threshold, this is the function I'm using with, I'm claiming that I'm only counting the vertices of this order. So if I calculate that function, I'm simply interested in how many are there and what's the probability that I connect to them. And the product is the trade-off I've been talking about. So there are this many of them, and you highly likely connect to them. You made that point, so it's a constant. I'm leaving out a lot of details here, but it will be this order, and that's why it's not surprising that if you divide by that order, that it's converted to a constant. Okay, that's also the reason why there's likely to be a connection between a triangle and the nearest neighbor degree. So if you think about two neighbors, then the probability that they connect with each other, you could think that you could just put that in that connection probability. And in fact, that is true. If there's no structural correlation, or if you have enough freedom, you could claim or even make rigorous that the clustering coefficient is the neighbor function squared. And this has been reported in the literature quite a few times. And do note that this is true only when the weights are bigger than square root of n. So it means that in the tail, you'll get the tail of the h function squared. And indeed that's true for all the models we've looked at. Finally, final 5 minutes, graphlet counting. Ongoing work. This will take us a bit more time to complete this because it's getting messy, as I'll show you. Who knows what graphlets are? Can I see hands? Who knows it? A couple of people. Motifs? Yeah? Okay, graphlet motifs. So here you see a graphlet. So I'm looking for an induced subgraph that you could detect in my bigger graph. So this is the particular graph that I'm interested in. You know, this could also trigger a square. This one also, if you take the union of these, that's the motif. But with the graphlets, I really want this structure, and I'm not happy with an additional edge in between. That's the difference. The results I'll show you will hold for graphlets and motifs. And obviously, we've been talking about the triangle, and that's a graphlet, yeah? A particular one. Or a clique. Okay, what's the connection? I'm going to show you now the final part, but what's the connection with the first part? I guess when analyzing the spectrum, I've made the point that some of these triangles are the least likely, where you think in terms of a trade-off between occurrence of certain nodes and actually making the connection. I'm going to use the same reasoning here. So I'm asking, I want to count or detect a graphlet like this, triangle or a square or whatever. You give me a graphlet and I want to say something about it. And in the large n limit, so for large networks, we're able to tell what the order of the nodes should be for the dominant graphlet to occur. So if you find a graphlet with high probability in a large network, it will be of that type of composition. That's the idea. Okay, so we've done this calculation before, but now with a general alpha. So you're willing to believe me that this is the order. This is exactly what we just saw with the AND function. So how many vertices are there of order n to the alpha? The answer is order n to the alpha 1 minus tau plus 1. just as take that as a given. Then this is the most likely triangle that comes out of an optimization problem. So you just ask in the large n limit, what is the most likely triangle that can occur, and this is the only one that can survive. So all of the nodes should be of the order square root of n. I didn't really use this knowledge before because I had something like that this should be the product equal to n, but here when I'm asking for the most dominant triangle, it will have in a large network this configuration. And then the number of triangles is the number of square root n triples that you can find times the probability that they form a triangle. So if you plug in the number of them, and I need 3, and that connection probability, you get this order, and this is then the predicted number of how many of these triangles will occur in a large network. Yeah. And yesterday, Pim, Dima and I had an interesting discussion, and later I did some literature search, and this has also recently been confirmed in a paper where people study cliques, and of course a triangle is a clique. And it also confirms our result that we have for any complete graph. So that's nice. And the method that they're using is quite different. Okay, then final slides. Give me any graphlet, so any substructure of a network, and you could ask what is the most likely configuration. So then you would need to count the number of vertex sets that give the dominance configuration, and need to multiply by the probability that they're actually together forming this induced subgraph. Okay, so that's a lot of reasoning, but similar as what we've seen for the triangle. Okay, don't want to explain that. And then you could start looking at graphs like this. So this is the complete graph on 5 nodes, and we can prove, and in fact for any complete graphs, all of these nodes will have the order square root n. But nasty things can happen. That's why I give you this example. So here are 2 nodes. So this is just a structure that you want to find in the network, right? Here are 2 nodes that are connected with each other, but also connected to 3 more nodes. Because they branch out, they have a bit more freedom. This is just intuitive reasoning. And that means that they can exist together. These are 2 hubs. They build a bridge, and then they connect to smaller nodes. And this will be the most likely configuration of that. And what we see in our analysis so far is that we only see order 1, that order. So the ranges that we saw on the spectrum. So finally again, the trade-off. You want hubs, but they're rare. You get small nodes for free, but they hardly connect. That's a trade-off. So you need to take that both into account. So here you see some examples. So we're working towards an atlas of graphs. It's a bit of an ambitious title, but we do need this because we can't find extremely general notions. But we are working towards classification of graphlets that have the same type of optimal composition. So here you see an example of a complete graph. Any complete graph we can do. Any circular graph we can do. And here you see also other examples that turn out to be optimal. So a hub with smaller degree nodes and even connected to a constant degree node. That's the so if you're asking for this graphlet, this is the optimal composition that we'll give it. Yeah, so now you're asking, at least we are asking ourselves, to what extent can we classify this? And we're quite far, but all of these are of these values that got meaning, I hope, in this talk, being the points where there's no more additional gain, let's say. And there are also still funny things, like this one. It does not have a unique optimum, we know this. So there are several combinations of degrees that will lead to the... So if you find one, it could be one of 2 configurations. And if you think about it, you can also understand it, understanding these structural correlations. But let's not go into that for now. So we're studying these graphlets, and this will take a couple more months. And it's very much the same intuition as what we've developed for understanding the spectrum and the AND function. So final slide, takeaways if you like. Structural correlations, I think that's the word. There's one thing I want you to take away from this presentation, is that the moment you can only build an edge once, there will be structural correlation, preventing edges but also triangles from being created. And then the question is, what is then the best way to create it? We made a first step towards universality, but definitely want to explore this also in the hyperbolic framework of DIMA, for instance, to see whether it makes a difference. Okay, that final point, I just made it, and all the special points I showed you were also playing a role in that spectrum. That's a connection that's only vague now. That was it, so thanks.
Any questions?
I just wondered, how did you choose the function of the hidden variable model? Like it's h prime over n, but it could be something asymptotically just going to 1, but not attaining the threshold.
Yeah, exactly. So first of all, we chose it in the hidden variable model because it's simply the easiest one to work with. But you're right, there's some, it's a bit arbitrary because definitely there's a whole class of candidate functions that would fit in. So you also saw the e to the minus function popping up in the ECM model, and for that it should work as well. So we chose it to do the calculations, and we should still argue, and we have done this but not in the paper, that for the, let's say, the typical universality class of connection probabilities that people know, that the same spectrum occurs. Yeah. Yeah. Some question.
Yeah, so I like this popping up of this into the tau minus 2 over tau minus 1. Because if you look at the central limit theorem for Pearson's correlation coefficient in the erasure configuration model, you get exactly that.
Okay.
Up until some slowly varying function, depending on if you do pure power law or regular variable distribution. I was actually wondering, did you look at CLTs for this clustering coefficient? Because you mentioned CLTs for the A and D, but did you look at CLTs for the clustering coefficient?
Yes and no. I mean, we've done the calculation, but for instance, the stable law that we get, you don't get there. But it's definitely an interesting direction. I mean, you're working on CLT for the global clustering, I think. So yeah, proving more of a functional convergence could definitely be something to look at. But yeah.
But do you believe it's a stable law, or do you believe it's a normal law?
I believe it's quite stable, but not in that sense. I believe it's, what you find is really converging in probability, for instance, in most cases. So not with the triangles, you're quite stuck, especially if you go down that road. And that means that statistically it's quite reliable. And that's a bit counterintuitive to your recent work, for instance, where you, but indeed in the range where you are, it's probably you've proved it. It's not stable in the stable sense.
Yeah.
It's a good point, but we should talk about this because there's definitely more to do here.
The assumption you assume twice between 2 and 3, but 3 is not included. But when twice equal to 3 is also still free networks, right?
Yeah.
So why this is not included?
Yeah, I got the same question this morning. It's like one reason is that if we include it, take tau as 3, then you see that this point collapses with that point. So there cannot be a result, I would say, that says here are your 3 ranges. So for us, the fact that this range exists is really because there's always a distance, and that's also known, right? If tau is 3 is special, but definitely beyond 3, structural natural cutoffs collapse, and that means that, for instance, you could expect, I'm not even completely sure, but that you would just see a flat line.
Yes.
But even in this range, we do need the fact that there's a gap here, you saw it in the reasonings, for this behavior to occur. So that's why I'm saying, for now the results I'm presenting really need tau in between 2 and 3. Yeah, and there could be something going on in tau is 3 definitely, but you see it will be different than what I see. What I show you. Okay. And kind of the essence is out of the problem if we do that.
Can you go to your last slide, basically, where you the graphlets and numbers of them? So, do you think there is any system here? So basically, kind of maybe some average degree. So, like, what would be the formula, if any, for the asymptotic number over them as a function of?
Yeah, I guess the system you're asking for is the classification we're looking for.
Yeah, the scaling behaviors as a function of maybe number of average degree. As a function of ages and
yeah. We can definitely talk offline longer about it. The stage where we're now is that we have a whole bunch of lemmas for classifications. For instance, complete graphs, always this, no matter how many nodes, you always have this order. We also understand where the log comes from, but still it's a bit tailor-made work so far.
There is no system.
Yeah, there seems to be a system, but we're starting to explore them. It's just that we don't, at this point, get all the graphics, that we understand all the graphics. But we are, let's say, halfway. Yeah. I guess indeed this slide was also meant to show that there will be probably a system, but it will not be the prettiest system, because there's definitely in small variations a different configuration for it. Yeah.
Any other questions? Then let's thank you.
Thank you.